next we're going to cover L'Hopital's rule. L'Hopital was a French mathematician, and he actually did not come up with this rule. I believe it was a mathematician named Cauchy, C-A-U-C-H-Y, who came up with this, but L'Hopital bought it from Cauchy, so it's his. This rule states, well, first, this rule is used to find limits. We've been doing derivatives for a while, but it shows that we can use derivatives to find some limits. So the statement, if direct substitution for the limit as x approaches a of f over g gives 0 over 0 or infinity over infinity with whatever infinity signs you want, then the limit as x approaches a of f over g equals the limit as x approaches a of f prime over g prime. So if you want this limit, and you get direct substitution, if direct substitution gives you that or that, then you can use this rule which says that the limit you want equals this new limit, where you take the derivative of the top over the derivative of the bottom. And note, this doesn't say the limit of this quotient equals the quotient rule derivative. This says the limit of this quotient equals the quotient of their, well, equals the limit of the quotient of their derivatives. So let's look at 4 examples first. There are going to be 2 different ways we apply L'Hopital's rule. The first will be these 4 examples. Next will be later in this video. But I'd like to note, we haven't discussed limits as x goes to infinity. They will actually be the next video. We're going to use L'Hopital's rule to begin our understanding of limits as x goes to infinity. And a little more on them in the next video, but we'll be okay with this example because we'll have a graph. So let's start with the first example. This limit. Now, all of these L'Hopital's rule does apply to, but you do have to check that L'Hopital's rule does apply. Limit as x goes to 4, x squared minus 3x minus 4 over x squared minus 2x minus 8. Substitute 4. In any limit, if you can substitute and it gives you a number, then you're done. Substitute here, and we will see that we get a 0 over 0. 16 minus 12 minus 4, 0. 16 minus 8 minus 8, 0. Now, you could factor this. That's one way of doing it. I'm going to do it a second way. You could factor this, you'd get, I don't know, I don't feel like factoring it. Since you get a 0 over 0, I'm going to mark that by saying 0 over 0. We can use L'Hopital's rule, which I'm going to say equals by h, like that. It equals this new limit. Derivative on top, 2x minus 3. Derivative on bottom, 2x minus 2. Limit equals the limit of the quotient of the derivatives. Well, can we substitute here? Well, what happens? We get 8 minus 3 over 8 minus 2, 5/6. So that's okay. I guess that factored as x plus 1 over x plus 2. And then both had an x minus 4. So we use L'Hopital's rule to compute a limit. Let's look at another. Now we know from that supplemental squeeze theorem example that this limit is actually 1. But let's use L'Hopital's rule to show that. Could show with squeeze theorem as we did with that diagram. Let's use L'Hopital's rule. You substitute x equals 0, what do you get? Sine of 0. Sine of 0 is 0. Substitute x equals 0 on the bottom is 0. So you get 0 over 0, and you can apply L'Hopital's rule. And what do we get? Well, the limit equals this limit. Derivative of sine is cosine. Derivative of x is 1. What happens when we substitute here? Cosine of 0 is 1. 1 divided by 1 is 1. So again, we had a second way of doing that limit. How about this next one? E to the x, limit as x approaches 0, e to the x minus 1 over x squared. Well, try substitution. What do you get? 1 minus 0 minus 1. That's a 0 on top. 0 squared. So again, we get a 0 over 0. and we can apply L'Hopital's rule. Limit that we're given equals the same limit as x approaches 0. Derivative of the top, e to the x minus 1 minus 0 plus 0 if you want. Over derivative of the bottom, 2x. What happens here as x goes to 0? Well, you get 1 minus 1 on top, so that's 0. What do you get on the bottom? 2 times 0. So you get another 0 over 0. What happens when you get a 0 over 0? Well, you could try algebra, or you could use L'Hopital's rule. Let's use L'Hopital's rule. I don't know any algebra that would work there. So we'll apply L'Hopital's rule a second time. We can do that. And it equals this new limit. Derivative on top is e to the x. Derivative on the bottom is 2. And what happens when we substitute here? E to the 0 is 1, 2 is 2. So we get 1/2. Now how about this last one? Well, first, let's discuss a little what we mean by limit as x goes to infinity. We have e to the x. We have x squared. What would... Yeah, I'll leave it on the bottom. Limit as x goes to infinity of some function. Here's e to the x. Limit as x goes to infinity says, what does the function do as x keeps going in the positive direction? And in this case, for e to the x, you can see the function keeps going up. So in that case, the limit would be infinity. What if we had y equals 1 over x? Y equals 1 over x looks like that. Well, maybe I'll write what I said up here. Limit x goes to infinity, e to the x is infinity. What about limit as x goes to infinity of 1 over x? Well, what happens as x keeps getting larger? Well, this thing keeps decreasing. But does it decrease to negative infinity? No. It stops decreasing above 0. Keeps decreasing, never hits 0. So as x goes to infinity, 1 over x goes to 0. And we're going to keep things like that in mind for these, and we'll do a little more with them in the next video. But for our purposes here, we can interpret these using graphs. E to the 5x is the same as e to the x, but what, the x-axis is crunched in 5 times. So that limit as x goes to infinity is still infinity. X squared as x goes to infinity, well, we know how to graph x squared. X squared looks like that. So as x goes to infinity, x squared goes to infinity. You can also think of this, I mean, you shouldn't write it, but you can think of it algebraically a little. E to the infinity will keep going off to infinity. E to larger and larger numbers keeps getting larger. Numbers squared, as you increase those numbers, keep getting larger as well. But here, we have an infinity over infinity form. And we can apply L'Hopital's rule. The statement that's written is actually incomplete. This a could be infinity. So I'll just say that. That a can be infinity. What's the derivative on top? Well, it's e to the 5x, and then you use chain rule. So what do we get here? Well, we have a new limit to take. What happens as x goes to infinity here? Well, e to the 5x, again, is going to go to infinity by a graph like that top one. 2x is just a line with positive slope. So that's also going to go off to infinity. So we get another infinity over infinity form. And we can apply L'Hopital's rule a second time. Derivative on top, well, the 5 just carries along. And you have derivative of e to the 5x, which is 5e to the 5x. So we have a 5 times 5e to the 5x, which is 25e to the 5x. Derivative on the bottom is 2. You could actually pull those constants out if you want. And what happens here as x goes to infinity? Well, the top again goes to infinity. You know, a number like 25, that's not going to impact infinity. If there were a negative, it might. Well, it would. But 25 infinities is still going to be going off to infinity. And the bottom goes to 2, and infinity is not impacted by that 2. So this limit would be infinity. And we use L'Hopital's rule a couple times to show that. Let's look at the second type of L'Hopital's rule problems that we could see. For these second types of examples, we're going to make a couple observations. Recall, from the graph of 1 over x, which we discussed a few moments ago, and we also discussed in week 1, the limit as x approaches infinity of 1 over x is 0. And the limit as x approaches 0 from the right of 1 over x is infinity. Now, you can't actually divide by infinity, divide by 0. But if we treat these limits algebraically, so through, quote, substitution, we see the, quote, algebraic expressions. 1 divided into infinity equals 0, in quotes. And 1 divided by 0 on the right equals infinity. If you're on the left of 0, you get a negative. But these are just some observations. Now, 1 over infinity does not equal 0. We can only treat infinity as a limit. But it's useful to interpret it without a limit so that we can extend this kind of symbol manipulation to limits which take a form, in this case, 0 times infinity. Remember, L'Hopital's rule applied when you got a 0 over 0 or an infinity over infinity. Well, here, if we do a substitution and get a 0 times infinity, positive or negative, as in this limit, we can turn that into an expression to which L'Hopital's rule applies. And what symbol manipulation will we use? Well, I'll put big quotes here. 0 times infinity. Well, what if we write that 0 as a 1 over infinity? What do we get? Equals 1 over infinity times infinity. So all we did was take this 0 and write it as a 1 over infinity. And, well, if we just write these symbols as a fraction, we would get an infinity over infinity, and an end quote, an end big quote, and we can apply L'Hopital's rule to this form just by flipping this 0 around. What does that look like in an actual example? Quotes indicate that it's not true, but it's useful to see. One of the important things in calculus is actually seeing that 1 divided by infinity is not 0, because infinity is a limit. It approaches 0. But we're making these observations here to help us see what we're going to do for limits like this. Well, we have limit x approaches 0 from the right, x log x. It's a limit. Try substitution. What do you get? 0 times negative infinity. Why is that negative infinity? Well, you go to the log x function. As x approaches 0 from the right, log x keeps going down. So negative infinity. So here we have a 0 times a negative infinity. Well, we can rewrite that as an infinity over infinity. And how are we going to do that? You could take the infinity and flip it around like this and get a 0 over 0. I tend to find, especially in an example like this way easier. So what are we going to do? Well, our goal is to apply L'Hopital's rule, so let's rewrite this. I'm going to rewrite it here. Equals limit, x approaches 0 from the right. Why do we need 0 from the right? Yes, because log x is not defined at 0 or to the left of 0. So we can only treat this limit on the right of 0. So we took that x and threw it in the denominator. Now you can't just say it's log x over x. You have to be careful when you're throwing things in the denominator. Why does this expression equal this expression? Well, we have log x divided by 1 over x. That's the same as log x times the reciprocal of 1 over x. So log x times x over 1, which is x log x. Well, what happens when we do a substitution here? Well, it should be an infinity over infinity. Is it? Well, as x approaches 0 from the right, 1 over x approaches infinity from that graph. As x approaches 0 from the right, log x approaches negative infinity. So we do get an infinity over an infinity. So what does this equal? Well, let's see. Equals with L'Hopital's rule, we have an infinity over an infinity, a negative on top. What's the derivative of log x? This is one of those examples I find unlined paper much easy for with all these fractions and things. 1 over x is the derivative of log x. What's the derivative of 1 over x? Well, negative x to the negative 2, or you can remember that fractional form, negative 1 over x squared. We have a 4-tiered fraction. Before even thinking about taking a limit, let's just do some simplification. So what do we have? We have 1 over x times x squared with a negative over 1. What does that equal? Well, we have 2 x's and 1 x. So one of those x's will cancel, and you're left with just 1x, and that negative 1 is still floating around. And what happens as x approaches 0? What happens to x as x approaches 0? Well, negative 0, also known as 0. So this limit is 0. And note here, to apply L'Hopital's rule, we had to do a little bit of algebra, which we did in this first step. We did not apply L'Hopital's rule in this first step. We just flipped the 0 around so that we could apply L'Hopital's rule. Now this L'Hopital's rule type 2 section actually has there are 3 other forms to which we can use symbol manipulation to get our original limit into a form on which we can apply L'Hopital's rule. I might have lost myself halfway through that sentence. But let's look at a couple more observations. Now first, we're going to recall 3 limits using natural logarithm. We've talked about all of these at some point. As x goes to 0 from the right, log x goes to negative infinity. We just saw that. As x goes to infinity, log x goes to infinity. We saw that a moment ago. And as x goes to 1, log x goes to 0, because e to the 0 is 1. So with those in mind, we're going to consider limits which take a form 1 to the infinity, infinity to the 0, or 0 to the 0, well, and 0 to the 0. And remember, a logarithm can turn something with an exponent into a product. And as we've seen, products are much more convenient in calculus than exponents, in some sense. So we can introduce a logarithm to a limit which takes that form and turn it into a form to which L'Hopital's rule applies. Well, how can we do that? Well, again, we have 3 strings of equalities. These are all symbol manipulation equalities. What if we threw a log on 1 to the infinity? Well, we'd get infinity log 1. What's infinity log 1? Well, log 1 goes to 0. Infinity times 0. Well, that's the same as the last form we discussed, but just to finish the observation and turn into one, on which L'Hopital's rule directly applies, we can throw that 0 in the bottom, making an infinity times 1 over infinity, which is an infinity over infinity. So just by throwing a log on this and following the symbol manipulation, we get an infinity over infinity. What about this infinity to the 0? Well, what do we get? 0 log infinity. As x goes to infinity, log x goes to infinity. 0 times infinity, and then we can throw that 0 in the bottom. 1 over infinity times infinity equals infinity over infinity. L'Hopital's rule applies. What about 0 to the 0? What happens here? Well, we get 0 log 0. As x goes to 0 from the right, where it's defined, log x goes to negative infinity. So we have 0 times negative infinity. Well, we can rewrite that 0 as a 1 over infinity. For symbol manipulating purposes, we can do that. Times negative infinity. And I'll just move the negative because we're just moving symbols. And then, of course, that equals what? Negative infinity over infinity. So throwing a logarithm on these allows us to rewrite them in a form to which L'Hopital's rule applies. Maybe that should be on which L'Hopital's rule applies. Yeah, I think on is the better word there. And we'll end our quotes. You don't want to start quotes and not end them. So what do we have here? Let's do, now, as you can see from the symbol manipulation, the actual computation for all three of these forms is quite similar. So let's just look at two examples. Which one is this? This is a 0 to the 0. Yeah, let's do an example of 0 to the 0, infinity to the 0. Yeah. Or no. Yeah, let's do 1 to the infinity and 0 to the 0. Because that's the one that has an extra negative floating around. So here, what do we mean of the form? Well, I mean when you do a substitution. Here, you do a substitution, you get 0 to the 0. So what are we going to do? We're going to do a different limit. Remember, throwing a logarithm on something changes it. This is a new limit. But fortunately, we know how to get rid of logarithms. So we're considering this limit. Well, how can we rewrite this? Well, no, we can't rewrite it like that. We can't just get rid of our limits without taking a limit. I was going to write x log x. I would have lost credit. Limit x goes to 0 from the right. You can see here, I mean up here you didn't necessarily have to consider it from the right, but once we throw a logarithm on it, you do. Which is why it was like that initially. Limit as x goes to 0 from the right of x log x. We are now in oh, this is the one with the negative. We're now in this step. Yeah, that step. So what can we do? Well, we can put that 0 in the denominator and then apply L'Hopital's rule. Or we could just say this is the previous problem. Equals from previous example. What did it equal? No. From the previous example, that equals 0. Remember, we're doing this, and in doing this, it reduces it to the reduces it to a form similar to the previous example. And if you already have the work done, why do it a second time? This limit is 0. So what's this limit? Is it 0? No. We threw a logarithm on it and got a 0. So what does this equal? Well, we need to get rid of the logarithm. Usually when doing these, I like putting a star up there and saying, like something like that. How do we get rid of a logarithm? Well, exponentials get rid of logarithms. E to this equals e to that equals e to that equals the original. In other words, this limit is e to that 0, which is 1. Let's do one more. Which one do we want? X to the 1 over 1 minus x. And this one we did not already do part of, so we will do all the work. Limit. What was it? It was limit x goes to 1 from the right. Limit. These also apply for limits as x goes to infinity, as long as they take one of these forms. These forms, by the way, are called indeterminate forms. They can act like a lot of things. All of these forms on which L'Hopital's rule applies are indeterminate forms. Why are they indeterminate? Well, the first 3 examples we saw where we had 0 over 0, those 0 over 0s, that's not an equal sign. That's supposed to be a squiggly equal sign. Maybe even with 3 bars. A squiggly equal sign actually equals something. 0 over 0 acted like, in example 1, 5/6. 0 over 0 acted like, in example 2, 1. 0 over 0 acted like, not official notation, in example 3, let's see, what was example 3? A half. This is called an indeterminate form because it doesn't equal something, but it acts like anything. It can act like anything. How can it act like anything? A little off topic here, but that's okay. What does that mean? It can act like any real number. So let A be a real number. Can we get a 0 over 0 to act like A in the limit? I claim yes. I claim that how. I claim that's how you can do it. One of many ways. You could have also taken the first one and multiplied by 6A over 5, or the last one multiplied by 2A. Apply L'Hopital's rule. I will not ask you about that. But it is good to know. I remember in, some example with infinity, I forget the exact details, but it involved 2 balls are thrown into a room every second. Each second you throw 1 ball out. How many are left in the room after an infinite period of time? And the answer is you can make it any number. But let's do this limit. Why is it any number? Well, you want it to be 30? Put 30 of them behind you as 30 come in, and you can keep throwing the rest out. That's actually quite complicated, and something like that is very useful for understanding infinity. Because even though 2 are thrown at every second, you can throw all of them out of the room. Because you throw 1 away every second. Little off topic, but that's okay. Limit as x approaches 1 from the right of x to the 1 over 1 minus x. What do we get here? 1 to the 1 over 0. So 1 to the infinity. We can apply L'Hopital's rule. And what we're going to do is say that this equals with a star. We compute. Yeah, I know I said consider. That's why I wrote C-O-N. I guess I should say consider. Compute's a better word for it. We compute this limit. Limit as x approaches 1 from the right of log of x to the 1 over 1 minus x, and let's not write it incorrectly, 1 to the 1 minus x. Well, let's turn that into a product. This equals limit x to 1 from the right of 1 over 1 minus x log x. What happens if you try a substitution? Well, you get an infinity times an infinity times a 0. Well, we can write that as a fraction. We can take the infinity. This is one of those cases where, well, if we threw the logarithm in the bottom, we'd have to differentiate 1 over log x. That's annoying to differentiate. So this will be one where we throw the 0 into the infinity into the bottom. You could try the other way, and you'd get 1 over x over 1 over log x. Kind of a pain to differentiate, although not impossible. So what do we have? Log x over 1 over 1 over 1 minus x, which is just 1 over x. In this case, it looks like just combining the fractions. And what happens as x approaches 1? Well, we get a 0 over a 0. And then we can apply L'Hopital's rule. So 0 over 0, L'Hopital's rule, equals this new limit. We haven't taken the limit yet. Derivative of log x, 1 over x. Derivative of 1 minus x, negative 1. And this equals negative 1. 1 over negative 1 is negative 1. So our original limit is e to the negative 1. So try on the worksheet these examples. And it's when you do enough of them, you realize that the process you go through is basically the same. Now, some of the final limits could get quite complicated. I might put one of them. Yeah, I'll put one of them where after you apply L'Hopital's rule, the limit's a real pain. But there will be some where they follow similarly to these, where we apply L'Hopital's rule and then we maybe have to make a couple algebraic observations.